Gonna pick up where we were talking about last time, and last time obviously we were talking about chapter 2, which is measurements, and we talked about really units last time, maybe. But right, there we go. So we talked about units last time, and we we talked about some different types of units and the importance really of units. Remember that really when you take a measurement, it needs to have really, again, a number and also that unit, which is really, really important. So as we talked about in class last time, if you just put a number, like I think I used 100, I think the other day, really that number doesn't tell you much about what it represents. And that's why the unit part is really important. As we talked about, if that was $100, that's going to be very different than if it was, again, 100 pennies. I think I might even use apples, I think last week as well. So all that would be very, very different depending on the unit. So really important to always make sure unit wise that we always include units. So again, maybe it's something like 100 centimeters. We talked about last time really taking proper measurements and sort of how to do that properly. And remember, it is really based off of the piece of equipment that you make. So, whenever you take any type of measurement, there's always some degree of uncertainty with that measurement. So, there's some degree of uncertainty that happens when anybody takes a measurement. And the degree of uncertainty really is based on the equipment that you're using and really the scale that you're looking at. So, for example, here, if we were to look at sort of like that scale we looked at with like a ruler, where we have and again, say this was our centimeters. Remember that really, whatever piece of equipment that you are using, there's really kind of two things that you want to look for and basically identify. And that's going to help you really take a proper measurement. For example, you always want to kind of look at the large markings on your scale. And that large markings on your scale represent are usually sort of indicated with actual numbers. So usually those large markings will be indicated with numbers like we have here. So in this case, again, our large marking represents 1 centimeter. And then there should usually, in most cases, not always, sometimes your large markings are your small markings as well. There's only kind of one set of markings, but there's usually some small set of markings. And it's important, as we talked about, that you sort of count the number of small markings between those larger markings. And as we talked about in class, you want to make sure you always start counting really past the last large marking. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you do want to kind of stop counting once you hit the next big marking. So in this case, we had, as we kind of looked at last time, 10 small markings between our large marking. So if you're not sure, you can actually just divide the large marking by how many small markings you have. And that will tell you that each of those smaller markings, once again, represents 0.1 of a centimeter. So this would be 1.1, 1.2, 1.3, 1.4, 1.5. 1.6, 1.7, 1.8, 1.9, and 2 as we go all the way across. Now, when we talked about sort of taking measurements, there should always be a certain number of measurements that when anybody takes a look at the actual scale that you're using, so when anybody takes a peek at that scale, there really should be no sort of disagreement in terms of how much something is. So, for example, if we were to look at this particular scale here that we got going on, everybody should definitely agree that it is at least 1.3, right? So my marking there should definitely be past 1.3. And that would definitely be our certain number. So we would want to record 1.3. And when we do that, again, we always want to record all the certain numbers, and that's what this is sometimes referred to as all the certain numbers. But this is where our sort of uncertainty comes into play, and that is because it is not exactly 1.3 and it's not exactly 1.4. This is where sort of the estimation comes in when we take a measurement, or the uncertainty comes in when we take a measurement. So, for example, when we look at sort of the distance between these two markings, we have enough room there to sort of visualize, all right, is it like halfway there? If it is halfway there, you might record a 5 as that next number. Maybe you think it's less than half, so maybe you record a 3 or a 4. Maybe you think it's past halfway there, so you might record a 6, 7, or something like that. So in my case here, I'm going to say, to me, just quickly looking at it, it looks maybe a little shy of halfway. So I would record, say, a 4, and then as we talked about, always want to record our units with it. This 4 is what is sometimes referred to as your first uncertain digit, or sometimes referred to as your estimated number. And when we do this, and whenever you take any type of measurement, you should always look at the scale because it is different. Even if you happen to be using two of the same type of pieces of equipment, maybe you and somebody else standing next to you. If they were made by somebody else, they may even have some different scales than what's on yours. So even if they may be the same piece of equipment, they may actually have some different scales. So whenever we record all the certain numbers plus that first uncertain number, that again is really what makes up significant figures. So in this particular case, this number here would be 3 significant figures when we take that measurement. Now, a couple of things that we talked about. Typically speaking, on most pieces of equipment, you usually can go one more place to the right of the smallest marking, and that's usually the right place to take your reading. So as we can see here, smallest marking is the first decimal place. We're actually able to take the reading one more place to the right to the proper number of digits. Now, if you're not sure, just looking at it or looking at the scale, but if you feel very confident, for example, that you were able to sort of correctly identify what the smallest markings represent, you could always take the smallest marking, for example, and just divide it by 2. And when you do that, in this example, you'll get something like 0.05. The number here is not important for our application, but what is important here is that will basically tell you how far you should take your reading to when you take a measurement. So if you feel very confident that, hey, you identified what the smallest markings represent, and you're not 100% sure how far you could go, again, or maybe you forget, I could just go one more place to the right, you could just simply divide the smallest marking by 2, and it will give you always a number, but whatever that number is basically how far you could take your actual reading to. And then you could kind of double check yourself that way. Remember, again, it does depend on the situation. So if you had a scale like on a graduated cylinder, like we looked at as well last time, much better drawing, I think, today. I'm not sure. So maybe that's let's say these are milliliters, and we'll put our green Kool-Aid in here. Remember as well, we also talked about that when you do have a liquid inside something like a glass cylinder, like a graduated cylinder, you typically will again see this curvature of the liquid, which is known as the meniscus. And we always read when the meniscus looks like this, kind of the U-shaped meniscus, you always want to read from the bottom of the meniscus. And I would say, and probably 99 times out of 100, that is what your meniscus is going to look like. It's going to look basically kind of like a U shape. It is possible to have it going the other way, but most of the time it will look like this. So we still want to look at our scale here and really try to figure out what is going on in terms of our measurements. Here we have 10. Here we have 20. So on this particular scale, I'll just write it over here. Our large scale is 10 milliliters. We again are going to count the lines starting with the first line past that big marking. So that is 1, that is 2, that is 3, that is 4, and that is 5 markings. So once again, if you're not sure what the small represents, you could actually just divide the large by how many small markings you have. So that's really how many small markings you have. And that tells us in this particular case, each of our small markings actually represents 2 milliliters. So again, that would be like we looked at last time, 12, 14, 16, 18, and 20. So now when we take our reading, once again, coming from the bottom of the meniscus, as we talked about last time, in this particular case, we find ourselves somewhere between 14 and 16. And again, the number that is between 14 and 16 is actually 15. And that would be the best that we could do in this particular situation. And let's talk about why that is. Again, as we talked about last time, there really is not enough room within this little sort of space to figure out again where 14 ends and 15 sort of starts. We're able to kind of do that here because the difference here is really just 1 is basically the only difference. But over here on this particular scale, that's, we got a couple number difference between them. So we really don't know where it starts and where it ends. So that's really the best that we can do. That also means, like we talked about last time, that this measurement here would have 2 significant figures, with the uncertain number being our 5 in this case. And again, our certain number being the 1. And again, that's as best as we could do. So like we were talking about a second ago, if you took the smallest markings, which is 2 milliliters, and are very confident that, yes, I do believe this 2 milliliters is the smallest marking. Once again, if we divided that by 2, it'll be 1, basically. And that's a whole number. And that's exactly what we took this reading to. So again, you could really figure it out one of 2 ways, how far you should take the reading to. 9 times out of 10, you could go one more place to the right of the smallest marking. But this is a good example, like we did last time and sort of reviewed it here. It is possible that you cannot go one more place to the right of the smallest marking, and this would be an example of that. But again, if you just kind of take the smallest marking divided by 2, whatever type of number you get, whole number, take it to whole number, 2 decimal places, take it to 2, 3, take it to 3, 1 decimal place, take it to 1, and you'll be able to do that. The other really important thing that we talked about in terms of measurements and taking measurements is some very common mistakes that people make when they do take measurements. And that is for a lack of a better description, I always get it exactly on the nose. So remember that, if we take a graduated cylinder or something like this, and we'll do build a little bit bigger of a graduated cylinder there to help out. There we go. All right, so we got a little bigger graduated cylinder, and we'll just kind of borrow that there, cut it there on that line, and we'll call this 20. And again, here we would want to look at our scaling large numbers, 20 and 10 milliliters. So once again, our large marking going to be 10 milliliters. Once again, we're going to count our smaller markings starting here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 smaller markings and 10 milliliter difference. That means that each of the smaller markings is going to be 1 milliliter. So that's going to be 11, 12, 13, 14, 15, 16, 17, 18, 19. Now, I'm going to say, for lack of this example here, that the bottom of the meniscus is dead on the 19 right there. So we talked about this at the end last time. can we record 19 milliliters? Should we record 19.0 milliliters? Should we record 19.00 milliliters? And I think I asked the question last time in a slightly similar example, is there a difference in terms of each of these things? Are these measurements that you would record? And again, the answer is, as we talked about last time, there is a difference. So you want to make sure that you want to make sure that you do record it to the proper number of digits. So there was a question. The large markings here is 10 milliliters, and that is the difference between the marking of 10 and the next one that was actually marked, which is 20. So if we take 20 minus 10, that would be 10 milliliters. So the large markings represents a difference of 10 milliliters, and we get that by basically subtracting the two larger markings, which was before I wrote all the other numbers, it was technically the only markings on the piece of equipment. And if you subtract that, that's how we got to that 10 milliliters. So again, like I said, if you do have questions, feel free to shoot me a chat, or if you want to speak, you're welcome to do that too. And you can unmute yourself and just ask the question too if you like. But that's how we get to 10 milliliters. And again, by counting the smaller markings, we had 10 smaller markings, and that gave us 1 milliliter each. So in this case, the difference, as we talked about last time, is in the significant figures. So this number written like this would have two significant figures, which means, again, our estimated digit would be the 9 in this case. And the estimated digit, just a reminder, is not always the last digit that's written. It is the last significant figure that's actually written. So in this case, what we're saying is, again, I think it's 19 milliliters, but I think it might be 20, or maybe it's 18. So if we look at this, we're right on the 19 mark right there. So we're really nowhere near 18 or 20. That's a big range of error, basically. Now, when we look at this measurement recorded like this would actually have three significant figures, with our 0 being our estimated digit. And when we kind of record it like that, we're saying, I think it's 19.0 milliliters, but maybe it's like 19.1. Maybe it is 18.9 milliliters. And if we really do sort of take a look at it and we're able to maybe super zoom in, that's pretty much what we are seeing based on this scale. So based on this scale, that's pretty much what we are seeing. And that is why that is really the right number here. We'll talk why that's the right number in just a second. This is not the right number. Obviously, a lot less room for error. Now, this also illustrates a good point as well. Sometimes people think, well, maybe if I add some extra zeros, it makes it more chemistry-like, more scientific or something like that. It's a good deal. So if we did this guy, this is basically 4 significant figures, right? And it's actually this last 0 that would be our estimated digit. So if we went with that guy, that we're basically saying, I think it's 19.00, but maybe it's like 19.01, or maybe it's 18.99. Now you may say, well, isn't that better? Because we're talking about to the second decimal place here, basically. Well, the problem with this is, although it may be better in a sense because it is more decimal places, the problem is, based on this particular scale that you have on this piece of equipment, you don't have the ability to actually go that far in your measurement. So you're kind of just making it up going this far, even though it might be technically a little better of a measurement, but you have no way to truly doing that on this particular scale. So brings up a good point that, sometimes adding extra zeros, not necessarily the best thing to do. You want to really base your measurement on the scale that you have. So how do I know this is really the right one and the right way to do it? One more time here, if we take our smallest marking, which is 1 milliliter, which is a whole number, I could go one more place to the right, which puts me to the first decimal place. And that is clearly what we see here and the proper measurement. Again, if you weren't sure and you took the smaller marking, which is 1 milliliter, and just divided it by 2, you would end up at 0.5 milliliters. And again, the 5 is not important, but the 1 decimal place is, and it tells you how far that you could take this particular reading to. Any questions on that there? So as we talked about, remember that if you sort of lop off some zeros on something that's like perfectly on the marking, what you're doing is making your measurement a lot worse than it should be. And based on the scale that you have, you should not do that. Any questions on any of that stuff there that we kind of talked about last time? And again, like I said, if you do have questions, just feel free to type it in, or if you want to talk, you could unmute yourself and ask as well.
I have a question, sir.
Yeah. Yeah.
So I know you just said that the 0.5 isn't what matters, but the decimal place. But maybe just kind of help clear my head a bit. Is 0.5 the number you at least can go up to and can't go past, or again, it just doesn't matter and it's just only at one decimal?
Yeah, so technically, and you're talking about, I'm assuming this right here, right? This 0.5. And
Yeah.
yeah, so technically speaking, when you divide the smallest number by 2, you will sometimes see people write a measurement, something like this, like 19.0 milliliters plus or minus 0.5 milliliters. And it's sort of the precision of that measurement, sort of how, sort of like, the plus or minus, we usually assume it to be plus or minus 1. And the 5 here, for our purposes, is not really necessary to worry about the actual 5. It technically means that, it could be like as high as 19.5 or as low as like 18 point, whatever that would be, 5 in that particular case. Although in most cases, we do kind of assume it's like plus or minus 1. If you took a pretty good measurement, it should be pretty close to plus or minus 1. But really, I wouldn't worry about the actual 5 number, for example. But more importantly, you should use it as how far you can take the reading. So when we do that, basically that 0.5 is the first decimal place. And when you take your actual reading, that is how far you should actually take your reading. So if you take the small number divided by 2, basically you should just use that as a guide as to how far you could actually take that reading.
Thank you very much. I appreciate it.
You're welcome. I got some questions here. We'll just take a little quick look at them. Let's see. Yeah, so a couple of things just to clarify, which I think hopefully we'll hit all the questions there in the chat box. Let me just make sure. Let me actually turn the page here if I can get it to do that. There we go. So a couple of things. If you look at a scale like we were, and again, you could figure out the large markings, which are usually, once again, the ones that are marked on the actual scale. And again, in this case here, the large marking is 1 centimeter. The thing that you could do to figure out what the small markings represent is by counting how many small markings you have. So again, in this case, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you go, okay, I know the big markings represent 1 centimeter, and I actually have 10 smaller markings between them. So if you take the 1 centimeter and you divide it by 10, which is basically the number of small markings, what that number you get here when you do that is 0.1. And what that will tell you is what each of these smaller markings here represent. So each one represents a increment of 0.1 centimeters. And that's why we said, okay, this one then would be 1.1, one more 0.1 would be 1.2, 1.3, 1.4, and all the way up. Now, when we talk about dividing the smallest marking by 2, what we're actually doing when we do this is, in this case, we'll get something like 0.05. What we want to use this for is to figure out in the end, when you take your proper measurement using this scale, you know that your measurement should end not in the first decimal place, but in this example, the second decimal place. So that's sort of how we get to sort of all these values. The large marking is just simply reading the distance between one marking on the scale to the next large marking. The zero 0.1 centimeters, which is the small marking, can be found by dividing that large marking distance by how many small markings you have. And then if you take the small marking and divide it by 2, it will tell you without having to really think about it how far you should take your reading. So again, if I was using a scale like we did previously, we would want to take our reading to 2 decimal places. It doesn't mean that the ending number has to end with a 5. It just means when you take that reading, you have to take it to 2 decimal places. So again, if I had my little guy right there, I would record 1.13 centimeters. And again, I took it to 2 decimal places, and that is what this sort of number basically is telling me how far I should take the reading to. So I hope that hit everybody's question. I hope that was in there. All right. So why don't we do some more practice of taking some measurements here? I think we got some examples coming up here. All right. So why don't you take a second and based on this scale, why don't you give the proper reading of, it looks like a piece of wood there, I think. So give a proper reading what that wood should be. The chat box. So let's take a look at it. Again, we're going to take the same approach, and you really should take this approach regardless of the piece of equipment that you're using. You want to basically always look for those two things. So we want to again figure out what our large markings represent. And again, those are the markings that actually have numbers typically next to them. So, and we're really just looking at the distance between 2 of the large markings. And in this case, the distance between the 2 large markings is 1 centimeter. Now, in this particular case, we're looking for what the small markings represent. And if we look at this particular scale, there are really no small markings, no additional markings really on this scale. That means that the large marking in this case and the small marking are going to be the same. These are both going to be the same in this case, which means the small marking is actually 1 centimeter as well. And that does happen. Obviously, as you can see here, only got basically one set of marking. They have numbers and that's it. There's nothing marked in between anywhere here. There's basically nothing marked. There's no other markings. So here's what we could do. If you want right off the bat to make sure that you're going to record it to the right number of digits, I feel good that I identified the small marking correctly. I could divide that by 2 and I'll get 0.5, which is 1 decimal place. What that tells me is when I take my reading here, I have to have it to 1 decimal place. So I know for sure it looks like a 4, and that's like a certain number, right? And that clearly is not exactly 4, not exactly 5. And again, this is where the estimation is. So maybe you think this is halfway there and you record 0.5 centimeters, which looks like a lot of what I saw in the box, which is good. And this would be our first uncertain number. And once again, this number here would have, how many significant figures this number would have? Number would have, if I put the number back, should have 2 significant figures, right? And again, the estimated digit there is the 5. Now, I did also see in the chat box somebody put 4.4. Perfectly fine. Yeah, maybe you don't feel it's exactly halfway there. Maybe you think it's just a little less than half. The important part is you record 4.4, and that is the proper number of digits. So once again, dividing the smallest marking by 2 tells you how far you should take the reading. And in this case, we should take the reading to the first decimal place, which once again is typically what you do, which is 1 more place to the right of the smallest marking. So the smallest marking here again was 1 centimeter. We could go 1 more place there to the right. Any questions on that one there? And they agree, so that's good. All right, so why don't you do this one here? This one here is going to be, as we actually will take a look at since it's up there. Let's take a look. We have once again 4 and 5. Distance between these two, again, going to be our large marking, which is 1 centimeter. Now we do have smaller markings here, so we're going to do some counting, starting here at past the first large marking. So that's 1, 2, 3, 4, 5, 6, 7. If I can hit them, 8 and 9 and 10. That was some really bad highlighting, by the way. So we do have 10 markings here between the large marking. So once again, if you're not sure what that represents, so maybe you're unsure, like, okay, I got 1 centimeter and I got 10 markings. I'm not really sure what that means. Once again, you can just divide that large marking by how many of those small markings you have and just throw that in your calculator. And if you just take 1 divided by 10, you should get 0.1. And once again, that will tell you what each of the smallest markings. Now, at this point, once again, if you want to just right off the bat, you could usually go one more place to the right to take the actual reading, or again, divide it by 2, and that will tell you I need to take it to 2 decimal places. And that's exactly what we see here. That's 4.5 right there, the big mark right there. And again, it's a little past 4.5, maybe not exactly 4.6. So here they go 4.55. The uncertain number here are 5, and this guy would have 3 significant figures. Any questions on that there? So here we do have, again, the importance, like we talked about previously, that we do want to make sure that you do take it to the proper number of digits. So if we look at this scale, once again, our big marking is going to be 1 centimeter. And in this case, our big marking and our small marking is also going to be 1 centimeter, as again, there is nothing marked between them. So here, and a question was, why are we dividing the small one by 2? Do you have to do that? You don't have to do that. If you could just figure it out, you could do it that way. But when you take the smallest marking, you divide it by 2. And again, we take the smallest marking and divide it by 2. It gives us this number. And once again, the number is not important, but what it will help you for sure determine is how far you should take that reading to. So once I divide that smallest marking by 2, I know no matter what the situation is, whatever I'm measuring on this particular ruler, I need to end up with a answer that goes to the first decimal place. So that's why you might want to divide by 2. You don't necessarily have to do that. Again, in most cases, 99% of the time, you could just go, okay, the smallest marking is 1 centimeter. I could go one more place to the right. And that's usually what we just did here, because the smallest marking is the whole number. One more place to the right is the first decimal. Now, the importance of this is, like we talked about, we would not want to record just 3 centimeters, because 3 centimeters in this case would have, as you hopefully know, 1 significant figure, which means my uncertain number and my certain number are the same in this case. My estimated number is actually 3. So I'm saying I think it's 3, but it could be like 4, it could be 2. And once again, if you look at this piece of equipment or wood that's being measured, it's like nowhere near those two numbers, right? That is like a big old room for error everywhere. And you shouldn't do that, because again, on this scale, what we figured out by dividing by 2, for example, is we can have the ability to go to the first decimal place. So again, here, we don't want to do that, but we do need to maintain the 0 there to give us the proper number of significant figures. And this would be 2 significant figures, where the uncertain or estimated digit is the 0. And again, basically what we're saying is this 3.0, but it could be 3.1 basically, or like 2.9. Again, much smaller room for error. And that's really what we see on this particular scale. That's pretty accurate in terms of where that piece of wood actually is. So again, there was another question about why dividing by 2. Do you have to do that? You don't necessarily have to do it. but it can be very helpful if you just want to like right off the bat know how far I should take this sort of reading without having to maybe sort of visualize how far you should take it. You could just simply, if you could correctly identify what the smallest markings represent, then you divide it by 2, and that tells you how far you should take your reading to. Question on that again. All right, so why don't you try this one? So based on the scale here, and the numbers are a little bit to the right, so that's the 9 marking, that's the 10 marking, that's the 8 marking. All right, so how should we record the length here of the red line? So take a moment or two and see what you would come up. Let's take a look. I'm seeing some different answers popping in there. Hopefully the right answer is up there on the big board. So let's walk through this here together and see where we should end up. So again, we're going to kind of look at our big markings. So in this case, the big line there is 9. The next big line is 10. So once again, our large marking on this is 1 centimeter. Now we want to count really what the small markings are. So we're going to go that's 1 marking, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So again, if you have a 1 centimeter difference and we have 10 markings, that again means that each marking here is going to be 0.1 centimeters. And again, you could get that if you want by dividing it by 10, and it will kind of tell you that. So this first guy is really 9.1. Next guy is 9.2. Next one is 9.3. And really right about here, it does appear to be kind of right on that 9.2 line. So we do have a couple of options here. 9.2 centimeters I saw come through. Saw 9.20 centimeters. And clearly, since it's at the 9.2, I don't think that one's going to work since that's 9.4 in this particular case. So here again, we want to figure out how far, based on the scale that we have here, we could actually take the proper reading. So again, typically you could go one more place to the right of the smallest marking. And I know that because if I take the smallest marking again and divide it by 2, we will end up with this number, which is 2 decimal places. So the correct answer in this case would actually be the 9.20, which looks like number 3 there. And again, because of the scale that we have on this particular ruler, we have that ability to go to the second decimal place, which is one more place to the right of the smallest marking. And that's what we should do. Even again here, if we feel it is dead on that line, we have to put that 0. And again, it is because these are going to be our certain numbers. And this is going to be our first uncertain number. And really where the estimation is coming into play, this would have, again, 3 significant figures in this case. So what we're really saying here, again, is I think it is 9.20 centimeters, but maybe it is 9.21 or maybe it is 9.19. And again, that's a pretty good measurement there. And also, if we kind of look at the scale of what we see on the actual ruler, that's pretty close. Once again, here, if you went with this guy, you're basically saying, I think it's 9.2, but maybe it's like 9.3, 9.4. And that means it's, somewhere between these markings, which is a lot more error and incorrect based on the scaling that we see here. Question on that. Then let's talk now, since we've taken measurements here, we've done a few examples. Let's talk about really what significant figures are, how we count significant figures, and what is a significant figure and what's not a significant figure. Basically, significant figures typically come from measured sort of values, kind of like what we were just doing there. And typically, when you take a measurement, as we've been talking about, when you record all the certain numbers plus that first uncertain number, that is basically what significant figures are. Now, there are some rules for counting significant figures. and what numbers are considered significant figures and which ones are not. So let's go through some of these rules here. The very first rule is pretty much all non-zeros are significant figures. So all non-zeros are considered significant figures. So when you have a number like 4, 2, 3, 6, 7, by the way, when we go to count significant figures, we always want to start left to right, and we always want to start when we hit the very first non-zero number. So depending on what your number is, you always want to start left to right, and you do not start counting your significant figures until you hit that non-zero. So as soon as we hit here the 4, that is where we're going to start counting our significant figures. Obviously, that's a non-zero, 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 which means every single one of these, 1, 2, 3, 4, and 5, they are all significant figures. So that's really important, and it's going to be really important here in a second when we talk about zeros and what's going on. Don't worry about things don't worry really about significant figures until you go left to right and you hit the very first non-zero. So that is really where you should start counting your significant figures. So let's talk about zeros. And there's a few different types of zeros, and these are usually the ones that give people sort of problems. So first off, there are what is sometimes referred to as leading zeros. And leading zeros are not significant. So if you have something like 0.0001234, that's some creative numbering right there, I think. We're going to start counting here left to right. And I'm not counting yet because that's a 0. Still not counting, that's a 0. Still not counting, that's a 0. Not counting, that's a 0. There it is, my very first non-zero. So that is where I should start counting in this case. The rest of them are also non-zeros. So this guy would have 4 significant figures. The zeros in front, sort of like holders to hold everything. You could have like a million zeros in front. Hopefully you don't have a number like that, but you could have like a million zeros in front before you hit that very first non-zero number, and all those zeros would be considered not significant. So that's the importance, as we were just talking about, of you should not start counting your significant figures until you hit that very first non-zero. Now, the next type of zero are sometimes referred to as a trap zero or a captive zero. And these are zeros that are trapped between two non-zero numbers, and they are significant. So if I had 4003, once again here, I will start left to right and counting. So boom, right off the bat there, I hit my very first non-zero. So now I'm in my counting of significant figures. So for significant, we got a couple of zeros that is also trapped between another non-zero. So these are zeros that are trapped between two non-zeros. So they are significant. And my 3 is a non-zero. So that's significant. So this guy would have 4 significant figures. Any question on that one there? So that brings us to really the one that, well, frankly, people screw up on a lot and don't like. And this is the third type of zero, which is sometimes referred to as a trailing zero. And these are zeros that come at the end of the number. And these zeros may or may not be significant. So these zeros at the end may or may not be significant. And in this particular case, what makes them significant? So they will be significant if there is a decimal place in the number. So if you have or I want to say place, I guess, a decimal point. There we go. That's a better word. If you have a decimal point anywhere in the number, it does not need to be right next to those zeros. It could be far away from those zeros. But as long as there is a decimal point in that number anywhere, all the zeros that come at the end will then become significant. If there is no decimal point in the number, then the zeros at the end will not be significant. So, for example, if we got our friend 600 here written like so, how many significant figures will this number have? I see one, I see threes. This number written like so would have one significant figure right there. There is no decimal point written in this actual number. And when you're counting significant figures, I know sometimes we're like, hey, don't we just kind of assume it's there? Not for significant figures. So for significant figures, it needs to actually be written there for it to be significant. And if it is not written there, then it is not significant. So we do that for scientific notation. We kind of make the assumption like, hey, it's at the end, and that's fine for scientific notation. But for counting significant figures, it actually has to be written in a number. That means if I wrote 600 like this, how many significant figures would this one have? That is correct. I see coming through. It would be three significant figures in this case. Once again, we would follow the same sort of format. We would start counting here. These guys right here are really the zeros. I guess I mean a sort of a smiley face there. These guys right here at the end are zeros at the end. They are going to be significant because of the decimal point that's written. So this guy would have three significant figures. Yeah. Now, if I wrote a number like this, 12,000, how many significant figures would it have? Two. I like it. Yeah. Two would be right. It would be two. Once again, all these zeros at the end would not be significant in this case because there is no decimal point actually written in the number. The one and the two would be our significant figures in this case. Once again, counting from here. All right. Double Jeopardy question is which digit here is the uncertain digit? Uncertain number or estimated digit? Which one is the estimated digit or the uncertain digit in this case? That is correct. It is the two. So it is the two here that is the uncertain number in this digit or the estimated digit. This is a significant figure. This is a significant figure. This guy has only two significant figures, which means that's my certain number. That's my estimated number, right? Or uncertain digit in this case. So I think I might have said it last time, but in case I didn't say it, the uncertain number or the estimated number is not always the last number that's written in the number. A lot of times it is, but it may not always be the last number written. The estimated digit or the uncertain digit should always be, though, the last significant figure that is written. So in the case of the way I wrote it like this, that is the last significant figure that's written, and that is where my estimated digit. All right, estimated digit on these two, which ones? On the left, the estimated digit is what we think. On the left, the estimated digit is the 6. Yes, I would agree. Once again, it has only one significant figure, which means that's both the certain and the uncertain number. That would be my estimated digit. Guy on the right, my estimated digit would be Our uncertain digit would be this 0 right there, the last 0, as that is a significant figure there. Any question on those there? So let's say then we had, this number here, 0.000320004002000, and we'll go centimeters. I'm not quite sure how you made that measurement, but we'll go with it. How many significant figures are there in this number? So take a moment and count it. I'm going to do the same because frankly, I was just writing numbers, so I'm not really sure how many there are. So take a moment and try to figure out how many significant figures we would have in that number. Good amount of numbers, 15, 12, 10. All right, so let's try to figure out here what the right answer is. And I'm going to do it with you because, again, I just kind of wrote numbers. So let's see what we got. All right, so clearly we always want to start like we've been talking about, left to right. So I'm going to start here. And frankly, that's a 0. I have not hit a non-zero. I'm going to go here. By the way, still a 0. Haven't hit a non-zero. Haven't hit a non-zero. Haven't hit a non-zero. Right there at the 3 is actually where we should start counting. That is our very first non-zero in this extremely large number, or a lot of numbers I wrote there. All right, so that's where we're going to start counting. So that is technically significant figure number 1. Next to it is a 2, which would count as a significant figure since it's a non-zero. We then have a 3-pack here of zeros, which are trapped between these 2 non-zeros. And that means trapped zeros are significant. So that would be significant as well. 4 is a non-zero, which would be significant. We have another 3-pack of zeros that are trapped here between 2 non-zeros. So those would be significant. That is a significant figure as well. So just keep track of where we're at this point. We got 1, we got 2, we got 3, we got 4, we got 5, we got 6, 7, 8, 9, and 10. So that leaves us just these zeros right here at the end, right? So are they significant? Yes, no, what do you think? I would agree with yes, they actually are significant in this case. And they're significant because way over here, there is a decimal point. So this is a very exaggerated example of the decimal point does not need to be right next to those zeros. They are technically significant numbers or zeros because of that decimal point being present. I lost track there, but I think that is 12, if I am not mistaken, in this case, in terms of our significant figures. Now, very often people will have this question. Maybe you have this question out there. So let me see if this is maybe a question somebody might have. Why are these zeros, which come after the decimal point, not significant? They are not significant because I have not counted yet and started counting my significant figures. So you would be correct. They are considered lead zeros at this point. So even though they do come after the decimal point, we have not started counting our significant figures until we got to here. And as you correctly said there, that would classify these guys, even though technically they come after the decimal point. That would classify them as leading zeros because once again, we have not hit the very first non-zero. Any questions on that one there? Now, something that we talked about, I think, in chapter 1, when we were talking about scientific notation, are n times 10 to the n, all right, in scientific notation. Remember that when you write a number in scientific notation, all the numbers before the times 10 part are always going to be significant. So all these numbers here will always be significant. So if we did have something written as 1.25 times 10 to the 3, remember that when we go to count significant figures, we're going to look at all these guys that come before the times 10 part, and this guy would have 3 significant figures. If we had 9.2 times 10 to the minus 2, once again, we would look at it here, and that would have 2 significant figures. So remember that when you write a number in scientific notation, any number that comes before the times 10 part is always considered a significant figure. And that is how, again, as we might have talked about last time, how you should assign significant figures is based on how it is written in scientific notation, not turn it into a sort of regular number, decimal type number, and then try to assign the significant figures. It is written in scientific notation specifically with those amount of significant figures, and that is where you should look at it. So remember that we also talked about that, sometimes the only way to record a number properly, in terms of the proper number of significant figures, which we're going to talk about here, is to write in scientific notation, because again, you could kind of control how many significant figures you need. So going back to that again, that 12,000 example, if I wanted to write this guy with 3 significant figures, or with 3 significant figures, there is no way that I could write this guy properly to 3 significant figures. Again, if you did 120 and put a little decimal there, that is 3 significant figures, but there is a very big difference, right, between 12,000 and 120 in terms of the meaning of that number. So although we hit the right number of significant figures, we basically just made the number wrong in the sense of what it should be. So you could do whatever you want with this. You could put a decimal point at the end. That's now 5 significant figures. There's just no way to turn this guy in sort of positional notation or decimal point form into 3 significant figures. So the only thing that you could do if you had an answer, and this was like your answer on the calculator or something like that, and you needed 3 significant figures, you would have to turn it into scientific notation by going 1, 2, 3, 4 places. 1.20 times 10 to the what did I go there? 1, 2, 3, 1, 2, 3, 4 places. And again, why would I not write 1.2000 times 10 to the 4? That would have how many significant figures if I wrote it like this? This would have,
5.
it would have 5 significant figures, correct? Yeah. And again, a situation where maybe adding zeros is not beneficial or correct in this case. So that would have 5 significant figures. This would have 3. And again, if this happened to be sort of your answer on your calculator, there is no way to get it to 3 significant figures without using scientific notation. So as we talked about last time, you don't necessarily have to write every answer in scientific notation, but you do have to write every answer to the right number of significant figures. And sometimes the only way to achieve that is to basically write it in scientific notation. All right, so let's take a look at some of these here. So looking at some of these rules that we just talked about here, those are all non-zeros. So we got 2 significant figures. These are 5, as they're all non-zeros. Here we have a 0 between 2, it's significant. Also between 2 non-zeros makes them significant. Here, no decimal point written, which means the only number that's significant is the 5. Here, the decimal point is there, which means those zeros at the end will become significant along with the 1 and the 6, which would be there. This is our scientific notation, so that's going to be 2, and this guy will be 3. And once again, all these leading zeros not significant until we hit the very first non-zero. And here's the first non-zero. And these are zeros at the end, but no decimal point written. So just the 8 and the 5 in this case would be significant. So looking at these, once again, all significant, starting counting at the 3. All 4 of those would be significant. Counting up the 5 and the 6 would be significant. starting counting at the 6 all the way through non-zeros and all the way through non-zeros. All these guys would be significant. Here's our trapped zeros. Once again, these guys would be significant because it's trapped. So all these guys would be significant, which would be 4. Same thing here, be 3. Here again, we're not going to start counting until we hit the 7. We then have the 0 that is significant because it's trapped, and the 2 is significant. And that would give us 3 significant figures. Here, we're not going to count the first 0, but we'll start counting here at the 4. And all these are trapped zeros along with some non-zeros there, which means that they're all going to be significant, which would be 5 significant figures. Any questions on those there? And lastly, our zeros at the end here, we got no decimal point written. Means my 2 is going to be significant only. Decimal point is written, so it means all those zeros there are going to be significant, even the one before the decimal place, because it is a trailing 0. There's nothing, no other number after it other than zeros. So all 4 of those guys would be significant. And once again, here, starting to count at the 4, this 0 going to be significant because of the 0, the decimal point there. Here, starting to count at the 2, and the other 2 is significant. Here, not counting until we get to the 3, and that is the only significant figure here. All right, and again, significant. These are not significant as there's no decimal written. Significant, not significant. Significant, all these guys being non-significant or not significant as there's no decimal point written. Once again, these are all 3 really good examples of estimated digit, where each of the estimated digit would be. Once again, in this case, this would be our estimated digit because it has 2 significant figures. That would be our estimated digit, and that would be our estimated digit. So once again, we get some of these trailing zeros at the end that are not considered to be significant. Once again, your estimated digit or uncertain number will not necessarily be the last one written. So again, in each of these cases, we see that the estimated digit or the uncertain digit is not the last one written. And obviously, here's our scientific notation as we talked about there. So everything before the times 10 part significant. We got 3, 2, and again 5. And we're going to look at it before we convert it into decimal points or anything like that. By the way, when we do convert it into decimal point, we do want to maintain the proper number of significant figures, and you want to make sure you don't sort of lose significant figures as you go back and forth. Once again, you might not be able to convert it properly because of no way to do it to the proper number of significant figures. So that is what this is talking about here. This written like the 500 with the decimal point means that these zeros are going to be significant. So it has 3 significant figures. Once again, we would keep those zeros if we transfer it to scientific notation to maintain the proper number of significant figures. This entire thing has only one significant figure, which is the 4. And that is why we do drop all those zeros when we put it into scientific notation. Because again, if we put it in scientific notation as 4.00000, we have something like 6 significant figures, which is too many. We should not gain significant figures as we do that. And here we have 2 significant figures, and we want to maintain those 2 significant figures. So really important as you go from, say, positional notation or regular number to scientific notation or scientific notation back to a regular number, that you really do just make sure you maintain the significant figures correctly, and they should be the same technically, no matter which way you go. All right, so take a moment here and for each of these, figure out how many significant figures there are, and what zeros are significant and which ones are not is what we're looking for here. And then write each of these in the proper scientific notation with the correct number of significant. Okay, let's see how you're doing. So we'll start with the first one. So maybe we just want to first identify how many significant figures there are. So again, we're going to start left to right, and we're going to go until we hit the 2, and that 2 is again where we should start. And the 6 is significant. That's significant. So that leaves us this 0 at the end. Is it significant? And hopefully you came to the determination that it is, because there is a decimal point in that number. So those leading zeros before the 2 are not significant. The 0 at the end is significant because there's a decimal point written, which means now we're ready to turn it into scientific notation. I'm gonna get rid of all my scribbling here I did on it, I think. All right, so and I'm gonna put some new scribble on it. There we go. We're gonna go 1 place, 2 places, and 3 places, and that would give me 2.650 times 10 to the 1, 2 minus 3. Remember, it's a small number, which means it should have a negative exponent. It has our 4 significant figures, which is what it should have in this case. Looking at the next one, we're going to start counting right there. So that's a non-zero. That also is significant. That's a trapped 0, which makes it significant. That's significant. That's significant. That's a lot of counting there. That's 5 significant figures I think we got going on in this guy. The 0 here, the only 0, is significant, obviously, in this case. To get us to a number between 1 and 10. So remember, proper scientific notation does need to be a number between 1 and 10. That would mean that you should write 4.3026, as they are all significant, times 10 to the 1, and the units would be good on these. Grams. And again, it has 5 significant figures, and that is our 5 significant figures on that particular one. Lastly, here, starting to count here at the 1, as that's a non-zero. The 0 here is trapped between 2 non-zeros, which makes it significant. The 4 is significant. The 4 is significant. And now the question is, are these zeros at the end significant? Yes, no, what do you think? Are these zeros significant? These zeros at the end are not significant. That is correct, as I see. Very good. And that is because, once again, there is no decimal point written. So remember 2 different things here. When we do scientific notation, we assume the decimal points at the end. But when you are counting significant figures, it does need to be written for you to count it. And in this case, it is not. So we're going to only have, in this case, that looks like 4 significant figures, which would take us through here. And we would go 1 place, 2 places, 3 places, 4 places, 5 places, 6 places to the left. We would have 1.044 times 10 to the 6. I think that's what I counted. And it would be liters. Once again, that would be our 4 significant figures. Any question on those there? Hopefully they agree. I think they do. So that's good. All right. So let's talk about another type of number. So up until this point where we talk about significant figures, these are measured numbers for the most part. And measured numbers are pretty much what it sounds like. It usually comes from some type of measurement. They have a certain number of significant figures. Their other type of number that we come across is one that's considered an exact number. And an exact number is basically determined one of 2 ways. You could determine it by counting, or a definition, like 12 inches equals 1 foot. What is counting? The classic example is, in most books, they have a picture of a basket of apples. And if you had a basket of apples, you would not do any weird experiment to figure out how many apples you have. You would just simply count how many apples you have. Like our 2 baseballs that we see there on the screen, you're not going to try to figure out an experiment to figure out how many baseballs you got going on there. You're just going to simply go, I got 2 baseballs. I'm just going to count them. So exact numbers basically are achieved one of 2 ways: counting or by a definition. Probably in chemistry, the definition aspect of exact numbers is most often where you would come across them. As you can see here, obviously, if you had cookies, which sound really good right about now, and you would just count them, are 2 baseballs. This again is a definition. By the way, this is also what is referred to as an equality, as we'll talk about a little bit later on in the chapter. An equality is 2 values that represent the same amount of something, but they're on different scales, right? So when I say, hey, that thing is 1 foot long, or you say it is 12 inches long, it represents really the same amount of length or distance, whatever you want to call it. But they're on different units, right? Same thing like if I had $1 or 100 pennies, represents the same amount of money, just on different sort of units. Same thing here. 1 kilogram is 1,000 grams. That is a definition. And again, it represents the same amount of mass. If you have 1 kilogram of mass, that's the same as having 1,000 grams. So what is the deal with exact numbers and why is it important? Well, or not important, I guess, I suppose. When we come across exact numbers in calculations, and we're going to talk about when we do calculations, how do we know how many significant figures our answer should have, for example? We're going to talk about that shortly here, hopefully. So when we come across something that's considered an exact numbers pretty much could have an unlimited amount of significant figures. So you could basically call as many significant figures as you want for those kind of exact numbers. So because of that, when we come across an exact number in a calculation, we typically will ignore its contribution to our answer in terms of significant figures, because I may say, oh, I think I should have 4 significant figures. You may say 3. Somebody else may say 423, because technically they could have as many as you want because they're exact numbers. So where this will really come into play is when we talk about calculations. If you come across an exact number, you pretty much don't have to worry about sort of it in your calculation. Where most definitions of exact numbers come from is, if you remember, there was kind of 2 types of units that we talked about. There's like the US system or the English system that's sometimes referred to, which is basically what the US uses. And pretty much everybody else, as we talked about, right, uses the metric system. So if you are using any type of equality or conversion that comes from a metric to metric conversion, like anybody in this column, they're pretty much considered exact numbers. If you do anything that's an English to English or US to US sort of conversion, also considered an exact number. As we'll talk about as well as we go through this chapter, when you cross over, though, if you go from like a US to a metric or backwards, either way, you actually do need to take into account the significant figures in that part of the calculation, because it's not considered an exact number. There's one, as we will see, that is considered an exact number, that US to metric crossover, which is 1 inch is exactly 2.54 centimeters. So this is one of the sort of crossover English to metric units or equalities that you can still consider an exact number. But usually if you go English to metric or vice versa, you have to look at the significant figures, and we'll do some examples of that a little bit later when we talk about it. But you're good to go and don't even have to worry about if it's metric to metric or US to US or English to English, whichever way you want to kind of refer to that. So take a second here and look at these, identify each of these as a measured or an exact number. So if I have 3 coins, that should definitely be a exact number, right? I'm going to assume you're just going to look and count that. The diameter of a circle is 7.902 centimeters. That feels very much like a measured type of situation. 1 hour is 60 minutes. That's your definition, and that's going to be an exact number. So it's important to be able to identify measured exact numbers, especially when we do calculations, so you know whether or not you should even worry about it when you're giving your answer, and we talk about how to do that. So hopefully they agreed here. Let's get it to move, maybe. There we go. All right. All right, so take a moment for each of these. How many significant figures we got going on in each of these? Okay, so let's take a look, see how we're doing. So we'll kind of go through these. Once again, we're not going to start counting here till the 3. 0 at the end, significant because of our decimals. So 2 significant figures in that case. Going to start counting right here at the 4. That's a trap 0, makes it significant. 5 significant. Once again, 0 at the end, going to be significant because of the decimal point there. So that is 4. Nobody significant here because we have not started counting until we get to the 8, which would be our only significant figure there, which would be 1. And significant here at the 2, the 8, and once again at the end, going to be significant because of the decimal point there, which would be 3. Any questions on any of those there? All right. So I want you to do this one. Take a second here and answer each of these questions, and then we'll go through it. Okay, so let's take a look and see. We're looking for, on the first one, which one contains 3 significant figures? Well, let's just go through them each. I'm going to go with starting at the 4 all the way through significant. So that's 4 significant figures on that guy. These are not significant. Going to start counting here. All 3 of these would be significant. And that is scientific notation, which means it has 4 significant figures. So I like 2 there for our first one. All the zeros are significant. All right. Well, clearly these are not significant. So that eliminates that guy. All these zeros here are actually significant. So this one's good. And these zeros here are significant as well. So actually, it's 2 answers here. Both of those would actually have ones where all of them are significant in terms of the zeros. So more than one answer, I guess, in this particular one. The number of significant figures in this one is scientific notation. So again, we are not going to turn it into a number and figure out the significant figures. We're just going to look at it, and it's all those numbers before the times 10 part, and that is 3, which would be there. So it looks like it is 2, 2 and 3, and then 3 for the last one. Any question on any of those? All right, so we've done a number of what significant figures are, how to take measurements to the proper number of significant figures, how to count significant figures. So let's talk about a really important thing involving significant figures, which is what we do when we have calculations and how many significant figures should our answers sort of have. So in terms of significant figures in calculations, we do use a calculator there. Looks like a nice calculator. And the problem with a calculator, and just a friendly reminder, when you use a calculator, it usually will not give you your answer to the proper number of significant figures. So you should probably in no case report a final answer like all the numbers that it gives you. You do have to do some rounding to the proper number of significant figures. So let's take a look and talk about rounding first. The rules for rounding is sort of normal rounding rules. So when you do a calculation, you do have to do some rounding of those numbers to get it to the proper number of significant figures. So as you may remember or know, if you got 4 or less, and that is the number next to where you want to round. You basically just kind of drop all the rest of the numbers. If you're like 5 or more, and again, that is the number next to where you want to round, you round up by 1. So we want to make sure that we do rounding properly. So if we look at some answers here, we have 8.4234. And in the first case here, we want to get to 3 significant figures, and that would take us to the 2, which would be our third significant figure. We then would want to look at the 3. And in this case, we would drop the rest of it because it's less than 5. And that would give us our 3 significant figures here of 8.42. Now, if we wanted to go to 2 significant figures, we would again look at our second significant figure, which is the 4. We then would look at the 2, and we would also drop the rest of the numbers because, again, it's less than 5, basically. Same thing here. Third significant figure is there, but we're looking at an 8 in this case, which means we do round the 7 up to 14.8. And if we were going to 2 significant figures, that would be the 4. We would then look at the 7. And once again, it's above 5, so we would round that up as well to 15 in this case, which would give us our 2 significant figures. Lastly, 3 significant figures looks about right about there. We would look at the 6, which means we are going to round this guy up to 3260. That is 3 significant figures. We do not want to write 326 because that is 3 significant figures, but there is a big difference, right, between the meaning of those numbers. 3,000 versus 300, big difference in the meaning. So you don't want to do anything crazy. Here to 2 significant figures would take us to the 2. We would also round up, and we do have to keep the zeros there to maintain really what the value represents. We could also do scientific notation on each of those to get to the proper number of digits. So, for example, if I have 13,333 and I want to round to 2 significant figures, what should my answer be? So take a moment and write what your answer should be if you're going to round this thing to 2 significant figures in this case. Okay, so we got some answers coming in the box. So let's take a look at some of these answers that came through and see. So I think I saw coming through there like a 13. Maybe like a 13, 1.3. So 13,000. I even saw maybe a little scientific notation I thought floated by me there. Maybe, yeah. So 4. So we got 1.3 times 10 to the 4, I think. All right, so let's take a look at all these things. First off, let's take a look at each of these numbers that were written and how many significant figures there are. So we're shooting for 2 here, I think I said. So if we look at the first one, that is 2 significant figures. So that's good in terms of significant figures. 1.3 is also 2 significant figures. 13,000 written like this is also 2 significant figures. And 1.3 times 10 to the 4 is 2 significant figures. So I'm going to say yes in the case of significant figures. I'm going to say some of these should not be your answer. So let's just use a simple example of I owe you $13,333. And I tell you, I'm going to pay you 2 significant figures. Here's your $13. Or wait, even better, I will pay you $1.3. You're probably not going to be very happy with me, right? Because there is a very big difference between, say, $13,333 and, say, $13. So although it does have the right number of significant figures, that value has changed because of what you did with your rounding. Same thing with this one here at 1.3. Although, again, it has the proper number of significant figures, there's a very big difference in the meaning of the number 1.3 versus $13,333. Now, if I tell you I owe you $13,333, I'll give you about $13,000. That's not too bad. That's pretty much the same number. Maybe I get the $333 teacher discount, whatever it may be there, right? So we really didn't change the meaning of the number. It has the proper number of significant figures. What about 1.3 times 10 to the 4? That is okay as well, right? Because that is scientific notation. 1, 2, 3, and 4 still represents the correct amount of value for that number. So it's really important, and it's a very common error that a lot of people will make when they are sort of doing problems and giving answers is they rightfully so in their head have like, I need the right sig figs. I should give the answers the right number of sig figs, which is what you want to do. But they're so concerned on getting the right number of significant figures that they do what I sort of call extreme rounding, where we lop off a lot of numbers and we change the meaning of the numbers. So it's really important that you never want to change the meaning of a number by rounding. And you want to maintain, again, the proper number of significant figures. All right, so hopefully that makes sense. So try to avoid that. Again, it is a very common error that a lot of people make. So in this case, if we were going to write the correct value here, and our calculator gives us this number, and we want 3 significant figures or 2 significant figures, we would go with 3 significant figures first, which would take us to the 4. We would look at the 5 and actually round up in this case. And we should end up with 3.15 as our answer. Here we're looking at 2 significant figures, which would take us to the 1. We would look at the 4 in this case, and we basically would drop the rest of the numbers, and that would take us to 3.1. Any questions on that rounding? Again, we don't want to do any extreme rounding or anything like that. But we do want to follow regular rounding rules. So looking at this one here, take a moment, take each of these to 3 significant figures and see what you end up with. Take a look. So 3 significant figures. Again, you just want to kind of figure out where you should stop. So we'll start counting here. Significant, significant, significant. That is 3. We're going to look at the next number, which is a 7. So that means we're going to round up to 825 centimeters in this case. Next, we will end up at 3 significant figures, which takes us actually to the 2 in this case. And that means we look at the 4 and we would drop it. So 0.122 grams, right? And lastly, here we want 3 significant figures, 1 significant figure, 2 significant figures. There is no more numbers there. What should I do? I need to put a 0 in there, right? So we got to pop a 0 in there to give us 3 significant figures. So sometimes you do need to add a 0 again to maintain the proper number of significant figures. And we could, on this first one, put the decimal point there. And again, you don't necessarily have to, but that would be 3 significant figures. You would not want to put the 0 though, right? Because now you would have 4. So you want to make sure you don't put the 0, and you really don't need a decimal point in that particular case as well. Any questions on that? Yes, thank you. B should be 112. It's kind of like 0.122, but not so right. So let me get that. Thank you. Not bad. Only one number I threw in there wrong. I'll do the classic. Always just making sure you're paying attention. I didn't really screw up too much. Probably did. All right. Thank you very much. It should be 0.112. In addition to writing the proper number of sig figs, we probably shouldn't change the numbers either on our numbers. Other questions on that there? All right, so now let's get to, now that we understand hopefully properly how to round, let's do some calculations and what we should do when we do calculations. So there's really kind of 2 groupings of calculations that you do. You usually will either multiply and divide, or you'll add and subtract. And depending on what operation you're doing, you do a slightly different thing in terms of what your answer should have. So let's start with the multiplying and dividing. As it says here, if you multiply or you divide, the answer that you should end up with should be the same number of significant figures as the one that has the fewest number of significant figures. So the least number of significant figures, when you multiply or divide, is how many significant figures your answer should have. So let's say we do this math problem here and we punch it into our calculator, and there's our calculator display. We are multiplying first and then we're dividing, right? So we're multiplying the top, dividing by the bottom. So we are looking at significant figures. This guy has 2 significant figures. This guy has 4 significant figures, which means technically speaking, when we get the answer for the top part here, the top part should end up with 2 significant figures. It's the least number of significant figures. Now, technically, what we're going to do is take that top number, which has 2 significant figures, and we're going to divide it by the bottom number that has 3 significant figures. That means that our final answer should actually end up with 2 significant figures. And that means on our calculator here, we're going to round up the 4 and end up with 5.4 that has 2 significant figures. So if you are multiplying or you are dividing, your answer should have the same number of significant figures as whichever number in that calculation is the smallest number of significant figures. Now, when we add and subtract, it is a little bit different than what we do. And let's take a look at a couple more, I guess, before we get there. So here we're going to divide 8 divided by 2. That is 3 significant figures up on top, 2 on the bottom. Again, if you put in your calculator, it may not give you enough digits. We should end up with 2 significant figures here. So we will need to, 3 significant figures. That is 3 on top and 3 on the bottom, which means 3 is the correct number. And we do need to have 3 significant figures here, so we will have to add some zeros for 3 significant figures. Once again, each of these zeros are significant, along with the first number in each of these cases. So it is 3 significant figures divided by 3 significant figures. All right, so do this one here, or perform this one, punch into your calculator, figure out what the proper answer should be to the proper number of significant figures. Okay, so once again here we are multiplying first and then dividing. And by the way, you don't have to do both of these together. So if you're just multiplying or you're just dividing, you will do basically the same idea here. It doesn't really matter. So we're going to look at significant figures up on top, which is what you would probably do first. I'm going to put the right number in this time. That's going to be 3 significant figures. That's going to be 4 significant figures, which means, again, technically speaking, when you get the top answer of just multiplying 5 times 3.408, you should end up with 3 significant figures. You're then going to divide it by the bottom number that has 2 significant figures. And that means that your answer should end up with 2 significant figures. So once again, on your calculator, I think you get something like 8.52 when you do this. And this would then be centimeters. And we would look at 2 significant figures, which would take us to here. We're going to look at the 2 and we're going to drop it. And we should end up at 8.5 centimeters. By the way, unit-wise, centimeters up on top divided by centimeters on the bottom, they will cancel. And that will leave you centimeters up on top, which is how we get to that final unit there. Any question on that one there? All right. So once again, also an important thing to keep in mind, as it's sort of mentioned, the actual calculator does not always give you, again, the proper number of significant figures. All right, let's take a look here at adding and subtracting in this case. Fix that there. So when we add and subtract, what we are looking at is the number of decimal places. So not significant figures. So that is a very big difference between multiplying and dividing, where you do look at significant figures. When you add and subtract, you're actually looking at decimal places, and your answer should have the same number of decimal places as the one with the least number of decimal places. So when we look at it, we're adding these numbers. That is 3 decimal places, not significant figures. That is 2 decimal places, not significant figures. That is 1 decimal place, not significant figures. So our answer should go to 1 decimal place, which means we'll look at the 0 here when we round, and we should end up at 66.1. Now, that has 1 decimal place. How many significant figures does it have? This number has how many significant figures? It does have 3 significant figures. Yeah. And that is important for a couple of reasons. It is important because, for example, let's say you added all these numbers together and now you want to take that number and then basically multiply it or divide it by another number. So you do have to kind of switch from decimal places when you're adding and subtracting to, okay, now I'm going to take that number and multiply it or divide it. So now I got to switch to significant figures. So you want to keep those things sort of in mind as to, significant figures or decimal places. If we take a look at another one here, again, subtracting, so 2 decimal places, 1 decimal place. Answer should end up at 1 decimal place. We are going to look at the 9, which means we are going to round up, and that's going to give us 62.1, which is 1 decimal place. Also, again, 3 significant figures in this case. Now, we sometimes do these things together, right? So we could, multiply. Maybe do a little division. And maybe we do a little addition of 0.234. All right, so why don't you try that? Do this guy here, and how many, give the answer to the right number of places. I'll do it as well, since I just made it up. Okay, so let's take a look. I see some answers coming in. So another really important thing before we get to this example, for example, here, and we'll see how I did making up numbers. But speaking of rounding, if you are going to be doing a number of calculations in a row, for example, maybe you do one calculation and you get the answer, and you're going to take that answer and do another calculation and get an answer, and you're going to take that one, do the next one. If you find yourself doing multiple sort of calculations in a row, it's really good practice not to round too much until the very end. And the reason for that is if you round a little at the beginning, round a little at the next time, round a little bit the next time, by the time you get to the very end, your answer may be very, very different than the correct answer, because every time you round, you sort of move yourself a little bit away from the right answer every time you do that. So, as I do this problem, I'm personally not going to round to the very end. And you might get a slightly different answer if you do round earlier versus later. But in most cases, outside of like a significant figure, just straight significant figure sort of calculation, and most real calculations that you do want to sort of avoid rounding to the very end. You should definitely keep track of your significant figures as you're doing it, but you should try to avoid maybe a lot of rounding to the very end. So, for example, here we will be taking the top number there, and that's really where we're going to start. We're going to start and we're going to multiply. And on my calculator here, if I multiply the top, I got 1.2 times 3.25. I'm not sure how I did that, but we do get on my calculator 3.9. Now, technically speaking, significant figure-wise for my top number here, I am multiplying 2 significant figures by 3 significant figures, which means my top number really should end up at 2 significant figures. I'm not quite sure how I made up those numbers to hit 2 significant figures, but I guess I did, so that's all right. We're now going to take the top number, which is 3.9, which is 2 significant figures, and we're going to divide it by the bottom number, which is 4 significant figures, right? Those guys right there. So if I take that top number, 3.9, and divided by 0.0113. I'm going to get on my calculator this number here, which is 345. I'm going to write the entire thing here. You don't necessarily have to write the entire thing, but just to show you what's displayed on my calculator. Now, technically speaking, if this was the end of the calculation at this point, we would clean this up to two significant figures based off of that and that, right? So this really should end up right there at two significant figures. So if this was really our final answer, we actually should round, right, to 350, right? It would be basically what our answer should be if there wasn't sort of a second part to this, right? So there is a second part to this, which means we're now transitioning to adding, which means technically we're going to take this number and we're going to add this to it, right? Which means if I do take that number and add that to it without an extra decimal point would be good. I will get on my calculator 345.3667434. And maybe if I added it to this guy where I did round 0.234, we will have 350 plus 0.234. Going to give us 350.234. All right. Well, the last sort of calculation we did is adding, which means we should not look at significant figures, but we should look at decimal places, right? And technically speaking, this guy should end here, which means it should actually have no decimal places. This one has 3 decimal places, which means really I should take this to a whole number, right? Which would be 345, or if you use the rounded version, 350 in this case, as we would go to a whole number. So personally, if I was going to do this calculation, I probably would end up with the top number because I usually don't clear it in my calculator. I usually just kind of continue on with my calculator, what number's in there, but I do keep track of it. And really the one that should determine how many decimal places we end up with is actually the 350 number, right? Which is actually a whole number, no decimal places. So with no decimal places, that's the smallest number of decimal places, none. And we actually should end up with a whole number. So you should end up with something that's made up one as 345 or 350. I would be okay probably with both answers, depending. Again, in most cases, you probably don't want to round too much to the very end. Any questions on that one there? All right, so let's take a look then at some of these other ones that we got going on here. All right, so take a moment here, and what should a proper answer be? We're going to add these guys together. So what should we end up with here? Okay, so if we throw this into our calculator at this point, we end up with 104.409. Here we are adding, so we're going to look at decimal places. So 3 decimal places, 1 decimal place, which means we should go to 1. We're going to drop the rest of that, 104.4 milligrams in this case. That has 1 decimal place and 4 significant figures in this case. Again, that would be important if you continued on and did some type of calculation involving that number. Any questions on that one there? All right, so let's try one more here. Let's try 0.00320 times 1.2 times 10 to the minus 6 divided by 423. What should the answer be here? I will do it as well. We'll see what we come up with. Let's take a look at the top part here first, because again, that is typically what you would be doing. Remember, we also have a number in scientific notation, so we want to make sure we punch it in properly to our calculators we talked about previously. So again, just to do the top part, we would take 0.0032. We would hit the multiplication button because we're going to multiply it. We'd hit 1.2. Once again, make sure you are using your exponent button and also your negative button, right? And 6, and we'll hit equals. And that will give us basically what's going on there in terms of our top number. So we'll take 0.00320 times 1.2 exponent button negative 6, hit equals. And on my calculator, I'll be honest with you, on my display, I got this going on. I ran out of room on my calculator. We might have talked about it last time. I go 4, I think. I got the right number. 0, 0, 2, 4, 6. Now, technically speaking, we're just going to try to keep track of our significant figures here. We are multiplying, so this has 3 significant figures, which would be these guys. This has 2 significant figures as it's written in scientific notation. So although I don't really have it the way it's displayed here, I technically should have 2 significant figures on this answer. But I'm not done with my calculation, right? I'm going to now take that number that technically has 2 significant figures, and I'm going to divide it by this number that has 3 significant figures. That means that my answer here should actually end up with 2 significant figures. So I'm going to finish it out, and I'm going to divide that number by 423 and hit equals. And it will, on my calculator, give me this 9.078 01418 E minus 12. So remember that we are going to go to 2 significant figures here is what our answer should be. That would take us to here. We do need to round up. That would give us 9.1. I know we talked about it last time, but just to finish out and reiterate, when you see this on your display, that is the times 10 part of your number. You need to include that with your number. Otherwise, you do not have the right number. And also, when you write the number, you need to make sure that you do not use the E when you write scientific notation, but it should be the times 10 to the minus 12. And that should be our correct answer in this particular case. Question on that. So again, as we might talk about last time, sometimes people, when they look in their display, they sort of forget about this part, and that is the times 10 part of the number. You got to make sure that you do include it with your number. Otherwise, you technically have the wrong answer for your question there. Any questions on that one? Calculations with significant figures. I think that's a good stopping place, I think, for today.